Imagine this. The year is 2050. Humanity has achieved the impossible. We've built a spacecraft capable of reaching light speed, 186,000 miles per second, the cosmic speed limit, the ultimate velocity. You're chosen as the first test pilot. You board the ship, engines ignite, you accelerate, faster, faster. 90% light speed, 99%, 99.9%. You push the throttle to maximum, trying to reach that final barrier, 100% light speed. But something strange happens. The engines strain. The ship vibrates. Yet, you're not accelerating anymore. You check the instruments. 99.999%. So close. You push harder. The engines scream. Energy consumption spikes to impossible levels. But the speedometer won't budge. No matter what you do, no matter how much power you pour into the engines, you cannot reach light speed. Not because of engineering, not because of technology, because the universe itself says no. This isn't science fiction. This is physics. In the next 100 minutes, I'll show you exactly why we will never travel at light speed. Not someday. Not with better technology. Never. 5 fundamental reasons. 5 laws of physics. 5 walls we cannot break. Fair warning, this might crush some dreams, but it's the truth. Let's begin. Part 1. The Dream and the Barrier. The year 2065. A journey that can never happen. Picture yourself standing in the command center of humanity's greatest achievement, the year 2065. Outside the reinforced windows, a spacecraft gleams under artificial lights, its hull embedded with technology that would make today's engineers weep with envy. This isn't just any vessel. This is the Prometheus Initiative, humanity's answer to an age-old question: can we touch the stars? You've been selected. Out of 8 billion souls on Earth, your name appeared on the final roster. The first human being to pilot a light-speed capable craft. Your hands will grip controls that can theoretically push matter to its absolute velocity limit. 186,000 miles every single second. That's the cosmic speed limit, the ultimate barrier, the universal constant that governs everything from the smallest photon to the largest galaxy. The training took 5 years. Simulations, G-force conditioning, psychological evaluations. They tested your reflexes at velocities that would pulverize ordinary humans. You survived because you're not ordinary. You're the pinnacle of human endurance, intelligence, and courage. But here's what nobody told you during those 5 years of preparation. All of it was pointless. Not because you lack skill, not because the technology fails, but because the universe itself has other plans. Engines ignite. The acceleration sequence. The countdown begins. Mission control's voices crackle through your helmet speakers. 10 seconds. 9, 8. Your heartbeat synchronizes with the rhythmic pulses of the fusion reactor beneath your feet. This reactor doesn't burn chemical fuel like the primitive rockets of the 21st century. It harnesses the same process that powers stars, converting hydrogen into helium, releasing energy that could vaporize a city in microseconds. 5, 4, 3. The vibration intensifies. You feel it in your bones, in your teeth, in the liquid surrounding your spinal cord. 2, 1. Ignition. The acceleration hits you like a freight train made of pure force. Your body presses back into the gel-cushioned seat as the Prometheus tears away from the orbital platform. Earth shrinks behind you, a blue marble becoming a blue dot, then a blue speck, then nothing but a memory. You're moving faster than any human has ever moved. Faster than Apollo astronauts. Faster than Voyager probes. Faster than anything humanity has ever constructed. 10 seconds in, you've reached 10,000 miles per second. That's orbital velocity multiplied by 1,400. The moon, which took Apollo 3 days to reach, flashes past your viewport in 14 seconds. Mars, 4 minutes at this acceleration rate. Jupiter, half an hour. The numbers blur on your instruments as speed becomes something almost abstract. 20% light speed, the stars ahead begin shifting their colors, a phenomenon called aberration. Blue light from stars in front of you compresses, turning cyan, then indigo, then violet. Red light from stars behind stretches into deeper crimsons. Reality itself starts bending around your velocity. 40%, 60%, 80%. The Prometheus shudders with each percentage point. Engineers promised this vessel could handle the stress. They spent 2 decades designing alloys that wouldn't disintegrate under relativistic forces. They succeeded. The ship holds together beautifully. But something else is happening. The invisible wall, 99.9%. 90% light speed arrives faster than you anticipated. At this velocity, you're covering the distance from the Sun to Pluto in 6 hours. The entire solar system has become your backyard. Time dilation kicks in with brutal efficiency. For every hour you experience, 2 hours and 18 minutes pass on Earth. Your mission controllers are aging faster than you. Your family is growing older while you remain suspended in this relativistic bubble. You push the throttle forward, harder. The engines respond with a roar that transcends sound, becoming something you feel rather than hear. 95%. The ship groans. Warning lights flicker across your dashboard, not indicating failures but rather cautioning you about physical laws you're about to violate. 99%. So close now. Just one more percentage point. Just one final push to break through that barrier and touch the absolute. You slam the throttle to its maximum position. The fusion reactor behind you dumps every available joule into the engine bells. Plasma streams out at temperatures exceeding 10 billion degrees Fahrenheit, hot enough to ignite a star. The energy expenditure is obscene, wasteful, desperate. You're burning through fuel reserves that took a decade to synthesize, all in pursuit of that final 1%, 99.1, 99.3, 99.5. The acceleration curve begins flattening. You notice it immediately. The same thrust that added 20% per minute at lower speeds now adds fractions of fractions. 99.7, 99.8, 99.9. Then nothing. The speedometer locks. 99.99%. For nines after the decimal. You stare at it, willing it to change. You engage emergency thrusters. You divert life support power to engines. You sacrifice everything, every backup system, every safety protocol, all for that infinitesimal increase. 99.999%. 5 nines. The display adds another decimal place, mocking you. You're so close that the difference is measured in microscopic fractions, yet you might as well be trying to swim across an ocean. The gap refuses to close. Your instruments show catastrophic energy consumption. You've burned through 80% of your fuel reserves. The reactor temperature hits red line warnings. The ship's structural integrity begins degrading, and still you're stuck at 99.9999%. 6 nines, 7 nines, 8 nines. Each additional decimal place requires exponentially more power than the last, and you're running out of power to give. The universe says no, understanding the barrier. This isn't mechanical failure. Every system on the Prometheus functions perfectly. The engines operate within design parameters. The fuel burns with optimal efficiency. Your piloting is flawless. And yet you cannot, will not, shall never reach that final barrier. Why? Because the universe doesn't care about human ambition. It doesn't care about technological advancement or species-wide determination. The cosmos operates on laws more fundamental than engineering, more absolute than mathematics. These laws don't bend. They don't negotiate. They simply exist, immutable and eternal. Think about this for a moment. Really let it sink in. We live in an era where humanity has split the atom, decoded the genome, mapped the brain, and touched the quantum realm. We've overcome diseases that once devastated civilizations. We've built machines that think, telescopes that see the birth of galaxies, colliders that recreate the first microseconds after the Big Bang. We've proven, time and again, that human ingenuity can solve nearly any problem. But Lightspeed laughs at our ingenuity. It stands there, immovable, impossible, absolute. A cosmic wall built from the fundamental architecture of space-time itself. You could gather every genius who ever lived, give them unlimited resources and infinite time, and they still couldn't break this barrier, not because they lack creativity or intelligence, but because breaking it would require breaking reality itself. Some barriers exist to be overcome. Others exist to teach us humility. Lightspeed falls into the latter category. It reminds us that we're still bound by physical law, still subject to constraints we didn't design and cannot change. It tells us that the universe has rules, and those rules apply to everyone and everything. From bacteria to superintelligent aliens, from photons to galaxy clusters. This realization creates a strange emotional cocktail. Disappointment, certainly. Frustration, absolutely. But also something else. Something almost like respect. The universe has drawn a line and said, this far, no further. There's a brutal honesty to that. No false hope. No ambiguity, just clear, uncompromising truth. 5 walls we cannot break, the journey ahead. Over the next several sections, we're going to dissect exactly why this barrier exists, not with vague explanations or hand-waving. We're going deep into the physics, the mathematics, the fundamental nature of reality itself. 5 reasons, 5 walls, standing between humanity and light-speed travel. 5 laws that cannot be circumvented, bypassed, or ignored. First wall, mass. Your spacecraft, your body, every atom comprising your being becomes progressively heavier as you accelerate. Not slightly heavier, infinitely heavier. At exactly light speed, your mass reaches infinity. Infinity isn't just a really big number. It's a concept that breaks mathematics, physics, and logic. An infinitely massive spacecraft would contain more matter than exists in the entire observable universe. It would collapse into a black hole, devouring space-time around it. The universe prevents this by preventing light speed. Second wall, energy. Moving faster requires burning more fuel. Simple enough at low speeds, but approaching light speed, the energy requirements don't increase linearly. They don't even increase exponentially. They approach infinity. To reach exactly light speed would require infinite energy. More energy than exists in all stars, all galaxies, all black holes combined. You'd need to harness the total energy content of existence itself. Good luck with that. Third wall, time. Relativity teaches us that time is flexible, malleable, dependent on velocity. Move faster, experience time slower. At light speed, time stops completely. Not slow, not nearly stopped, completely frozen. For a photon traveling from a distant star to your eye, zero time passes. It's born and dies in the same instant. If you reached light speed, you'd experience the same temporal paralysis. No thoughts, no awareness, no existence as we understand it. You'd be frozen in an eternal now, unable to experience past or future because both concepts require time to flow. Fourth wall, causality. Cause must precede effect. Fire precedes smoke. Birth precedes death. Action precedes reaction. This ordering is sacred, fundamental to how reality operates. But faster than light travel creates scenarios where effects happen before causes, messages arriving before they're sent, consequences preceding actions. The universe protects causality by making light speed the maximum velocity for anything carrying information. Break this limit. Break causality. Break causality. Break reality. Fifth wall, space-time structure. Here's the deepest truth. Light speed isn't really about light. It's about the fabric of space-time itself. The universe updates at a certain rate, processes information at a specific velocity, allows causality to propagate at a defined speed. That speed happens to be what we call light speed, but it's really the speed of reality. Going faster than light speed would mean moving faster than reality itself updates. It would mean existing outside the system, outside space-time, outside existence as we define it. These aren't engineering challenges. They're not technological hurdles. They're fundamental properties of the universe we inhabit. Overcoming them wouldn't require better rockets or stronger materials. It would require rewriting the source code of reality, changing the constitutional laws of existence, becoming something other than physical entities bound by physical law. The hard truth, why this matters. You might be thinking, so what? Why does this matter? Why spend time understanding barriers we can't overcome? Why not focus on problems we can solve? Fair questions. Here's the answer. Understanding our limits is just as important as understanding our capabilities. Maybe more important. Limits define possibility space. They tell us what kinds of futures we can build, what dreams are achievable versus which are fantasy. They prevent us from wasting resources, chasing impossibilities. They redirect our efforts toward goals that can actually succeed. The light speed barrier tells us something profound about our cosmic neighborhood. The nearest star system, Alpha Centauri, sits 4.3 light-years away. Even if we built a ship capable of reaching 99.9% light speed, and even if we solved the fuel problem, the radiation problem, the life support problem, and the psychological problem of multi-year journeys, we'd still need over 4 years to reach it. From the traveler's perspective, time dilation would make it feel shorter. But from Earth's perspective, from their family's perspective, they'd be gone for decades by the time they made a round trip. The galaxy spans 100,000 light-years. That means light, traveling at its maximum speed without rest or deviation, takes 100,000 years to cross from edge to edge. For beings limited to subluminal velocities, intergalactic travel becomes something approaching geological timescales. Civilizations could rise and fall in the time it takes to complete a single journey. This has implications beyond travel. It affects communication, trade, culture, warfare, everything. Science fiction often depicts galactic empires with faster-than-light communication and transport. allowing central governments to coordinate across thousands of star systems. Reality permits no such convenience. If we ever establish multiple stellar colonies, they'll be effectively independent. Messages between stars will take years. Help will arrive far too late to matter. Each colony will develop its own culture, its own solutions, its own identity. The light speed limit shapes not just what we can do, but what kind of species we can become. It enforces isolation on cosmic scales. It guarantees that intelligent life, if it exists elsewhere, remains mysterious and distant. It ensures that the universe retains its vastness, its emptiness, its capacity to humble us. But here's the paradox worth contemplating. Would we really want it any other way? Imagine a universe without speed limits, instant travel, instant communication, no distance, no delay, no separation. Would such a universe feel sacred? Would it inspire wonder? Or would it feel small, conquered, domesticated? Maybe the light speed barrier, for all the doors it closes, opens others. Maybe limitation breeds creativity. Maybe boundaries create meaning. Consider the difference between ancient explorers sailing uncharted seas versus modern travelers booking flights online. Both involve going from place to place, but one feels profound while the other feels mundane. The difficulty, the risk, the uncertainty, these things transform mere transportation into adventure. Light speed's impossibility keeps the cosmos adventurous. It preserves mystery. It guarantees that some questions remain unanswered, some horizons unreached. None of this changes the physics. None of it makes light speed less impossible. But it reframes impossibility from frustration into perspective. The universe has rules. Those rules create the universe we inhabit. Change the rules, change the universe itself. Maybe we'd prefer different rules, but we don't get to choose. We're players in a game whose code we can read but not rewrite. The path forward, what we can actually achieve. So if light speed is off the table, what remains? What kind of interstellar future can we realistically pursue? First, subliminal travel. We can't reach light speed, but we can approach it. 99%. 99.9%. Each additional 9 costs exponentially more, but the first several 9s are theoretically achievable. At these velocities, time dilation becomes significant. A journey that takes a century from Earth's perspective might feel like a decade to the travelers. Still enormous challenges, still requiring technology we haven't invented, but not physically impossible. Second, generation ships. If we can't make journeys short, we make travelers long-lived. Build vessels large enough to sustain ecosystems for centuries. Launch them toward nearby stars. The people who arrive won't be the people who departed. They'll be their great-grandchildren. This approach trades speed for persistence. Slow, patient, multi-generational. Very human, actually. Third, hibernation or suspended animation. Put travelers in stasis. Let decades pass while they sleep. This solves the psychological problem, but not the physical one. Still need propulsion. Still need energy. Still need time. But the subjective experience becomes manageable. Fourth, probe swarms. Maybe humans don't need to make the journey. Send millions of tiny robotic probes instead. Let them reach nearby stars, study them, transmit data back. Slower than light, but faster than anything carrying living passengers. Less inspiring than human exploration, but more practical. Fifth, accept limitation. Build thriving civilizations on the worlds we can reach. Our solar system contains resources beyond imagining. Asteroid mining, Martian colonies, Jovian moon settlements. We could keep humanity busy for millennia without leaving the sun's gravitational influence. Maybe that's enough. Maybe the grass isn't greener in Alpha Centauri. Each option involves trade-offs. Each accepts the light speed limit as immutable while finding creative solutions within its constraints. This is mature thinking. Childlike minds demand the impossible and throw tantrums when denied. Adult minds work with reality as it exists. The light speed barrier isn't our enemy. It's a fact, no different than gravity or thermodynamics. We don't rage against gravity for preventing unaided flight. We build aeroplanes. We don't curse entropy for causing decay. We build refrigerators. Similarly, we shouldn't waste energy fighting light speed. We should acknowledge it, understand it, and design our future around it. This documentary will prove exactly why that barrier exists. Over the following sections, we'll explore each reason in detail, backed by mathematics, supported by logic, confirmed by observation. Some of it will challenge intuition, some will seem absurd, but all of it is true, verified by a century of experimental physics and cosmological observation. Buckle up. We're about to discover why the universe built a wall we cannot breach, why that wall is actually 5 walls stacked together, and why breaking even one of them would shatter reality itself. The journey starts with Einstein, continues through modern physics, and ends with a conclusion some find disappointing but others find strangely comforting. We know our limits. We understand our cosmic boundaries. We recognize our place. And sometimes that recognition is the most human thing possible. Part 2. When mass becomes infinite. Einstein's revolution. The equation that changed everything. 1905. A patent clerk in Bern, Switzerland sits at his desk during lunch breaks, scribbling equations on spare paper. His name is Albert Einstein. He's 26 years old. He has no laboratory, no research funding, no prestigious university position. What he does have is an idea that will revolutionize human understanding of reality. That year, Einstein publishes a paper titled On the Electrodynamics of Moving Bodies. Buried within its dense mathematical prose sits an equation so simple, so elegant, that it fits on a napkin. 3 symbols. 1 equals sine, 5 characters total. E equals mc squared. Energy equals mass times the speed of light squared. You've seen this equation before. Everyone has. It's printed on t-shirts, carved into monuments, referenced in movies and television shows. But familiarity breeds contempt. We've become so accustomed to seeing it that we forget how deeply weird, how profoundly unsettling, how reality-shattering this equation actually is. Let's break it down. E represents energy, the capacity to do work, to cause change, to make things happen. M represents mass, the quantity of matter in an object, the resistance to acceleration, the weight you feel when gravity pulls on you. C represents the speed of light, 186,000 miles per second. And that whole thing gets squared, multiplied by itself. Here's what this equation tells us. Energy and mass are not separate things. They're the same thing wearing different masks. Mass is frozen energy. Energy is liberated mass. You can convert one into the other. The equation gives you the exchange rate. And what an exchange rate it is. Because c squared, the speed of light multiplied by itself, is an astronomically huge number. Light travels 186,000 miles in 1 second. Square that, you get 34 596 trillion square miles per second squared. That's the conversion factor between mass and energy. What does this mean practically? It means a tiny amount of mass contains a staggering amount of energy. 1 kilogram of matter, if completely converted to energy, would release 90 quadrillion joules. That's equivalent to 21 megatons of TNT, more than the largest nuclear weapon ever tested. From 1 kilogram to 0.2 pounds. The weight of a textbook. The sun converts 4 million tons of mass into energy every second through nuclear fusion. 4 million tons vanish, transmuted into the light and heat that make life possible on Earth. The sun has been doing this for 4.5 billion years and will continue for another 5 billion. That's how much mass it contains, how much fuel it's burning. But here's where things get strange. If energy and mass are interchangeable, then adding energy to something adds mass to it. Not metaphorically, literally. When you heat water, you're adding energy, which means you're adding mass. An incredibly tiny amount of mass, too small to measure with any scale, but mass nonetheless. The water becomes heavier. This seems absurd at everyday speeds and energies. Heat water from freezing to boiling. You've added about 4.2 million joules per kilogram. According to Einstein's equation, that increases the mass by about 0.000004 grams, 40 trillionths of a gram. Completely unmeasurable, utterly negligible. But what happens when you add enormous amounts of energy? What happens when you accelerate something to relativistic speeds? The Lorentz factor, mathematics of impossibility. There's a term in physics called the Lorentz factor. It's named after Hendrik Lorentz, a Dutch physicist who discovered it before Einstein but didn't fully understand its implications. The Lorentz factor tells you how much time dilation occurs at a given velocity, how much length contraction happens, and critically, for our purposes, how much mass increases. The formula itself doesn't matter for our discussion. What matters are the results. Let me walk you through what happens to your mass as you accelerate toward light speed. We'll use percentages because they're intuitive. At 10% light speed, your mass increases by half of 1%. If you weighed 200 pounds at rest, you now weigh 200.5 pounds, barely noticeable. You could step on a bathroom scale and wouldn't see the difference. At 25% light speed, your mass increases by 3%. 200 pounds becomes 206. You'd notice it if you tried to do a pull-up, but it wouldn't fundamentally change anything about your existence. At 50% light speed, your mass increases by 15%. 200 pounds becomes 230. Now you're definitely feeling it. Everything requires more effort. Standing up, walking, breathing. Your heart has to pump harder. Your muscles strain under loads they used to handle easily. But you're still you, still functional, still human. At 75% light speed, your mass increases by 51%. 200 pounds becomes 302. You've gained 100 pounds without eating a single extra calorie. Your joints ache. Your spine compresses. You feel like you're wearing a weighted vest you can't remove. But you're still alive, still conscious, still capable of thought and action. At 90% light speed, your mass more than doubles. 200 pounds becomes 460. You now weigh as much as 2 normal people. Every movement is agony. Your skeleton wasn't designed for this gravitational load. But surprisingly, you're still not dead. Your body adapts. Blood pressure skyrockets. Your heart works overtime. You persist. Now watch what happens as we add those final percentage points. At 95% light speed, your mass triples. 200 pounds becomes 620. 3 times your normal weight. You feel like you're carrying 2 adult humans on your back. Every breath is labor. Every heartbeat is struggle. You're barely functional, but you're still there. At 99% light speed, your mass multiplies by 7. 200 pounds becomes 1,400. 7 times heavier. You now weigh as much as a horse. Your bones crack under the pressure. Your organs fail. You can't survive this. But let's pretend somehow your body could handle it. Let's keep going. At 99.9%, your mass multiplies by 22. 200 pounds becomes 4,400. You weigh as much as 2 cars. The ground beneath you cracks. You'd collapse through most floor structures. This is beyond survival, beyond adaptation, beyond possibility. But we're not done. We're not even close. The exponential nightmare chasing infinity. At 99.99% light speed, your mass multiplies by 70. 200 pounds becomes 14,000 pounds. 7 tons. You weigh as much as a small elephant or a large truck. The structural integrity of any spacecraft would fail. The engineering required to support this mass would be absurd. At 99.999%, your mass multiplies by 700. 200 pounds becomes 140,000 pounds. 70 tons. You weigh as much as a fully loaded semi-trailer, as much as a railroad car, as much as a blue whale. See the pattern forming. Every time we add another 9 after the decimal point, the mass multiplication factor increases by roughly 10. This isn't linear growth. It's not even exponential growth. It's something worse. Something that accelerates toward infinity with terrifying speed. At 99.9999%, mass multiplies by 7,000. 200 pounds becomes 1,400,000 pounds. 700 tons. You weigh as much as a large building, as much as a naval destroyer. Your gravitational field becomes measurable. Small objects nearby would feel attracted to you. At 99.999999%, mass multiplies by 70,000. 200 pounds becomes 14 million pounds. 7,000 tons. You weigh as much as a skyscraper, as much as the Eiffel Tower. Your presence warps space-time noticeably. Light passing near you would bend. At 99.9999999%, mass multiplies by 700,000. 200 pounds becomes 140 million pounds. 70,000 tons. You weigh as much as the Great Pyramid, as much as a small mountain. You're no longer a person. You're a geological feature, and we're still not at light speed. We're at 8 nines after the decimal. We could add 9 more, 90 more, 900 more. Each additional 9 multiplies the mass by another factor of 10. The numbers rapidly become meaningless. They exceed human comprehension. They dwarf anything we have reference points for. At 12 nines, you'd weigh as much as Earth's atmosphere. At 15 nines, you'd weigh as much as Earth's oceans. At 18 nines, you'd weigh as much as Earth itself. At 21 nines, you'd weigh as much as the Sun. At 27 nines, you'd weigh as much as the Milky Way galaxy. At 33 nines, you'd weigh as much as all observable galaxies combined. And you're still not at light speed. You're just really, really close. Closer than the width of an atom compared to the distance to the nearest star. But not there. Not quite. Not yet. Because yet never comes. At exactly 100% light speed, at precisely that mathematical point, your mass becomes infinite, not arbitrarily large, not incomprehensibly huge, infinite, a concept that breaks mathematics, a number larger than any number, a quantity that cannot exist in physical reality. The spacecraft scenario, making it concrete. Let's make this concrete. Forget about human bodies for a moment. Let's talk about spacecraft. Specifically, let's imagine a vessel massing 100 tons at rest. That's roughly the mass of the International Space Station. A substantial piece of hardware, but nothing extraordinary by space engineering standards. You want to accelerate this spacecraft to light speed. Let's watch what happens to its mass. At 50% light speed, 100 tons becomes 115 tons. You've added 15 tons. That's significant, but manageable. You'd need to account for it in your engineering, but it doesn't fundamentally change your design. At 75% light speed, 100 tons becomes 151 tons, still reasonable. Your spacecraft weighs about as much as a large commercial airliner now. Your engines need to work harder, but they can handle it. At 90% light speed, 100 tons becomes 230 tons. You've more than doubled the mass. This is where problems start becoming serious. Your acceleration rate drops. Your fuel efficiency plummets. But you push forward. At 95% light speed, 100 tons becomes 320 tons. Triple the original mass. Your engines strain, warning lights illuminate, but the ship holds together. At 99% light speed, 100 tons becomes 700 tons, 7 times heavier. Your spacecraft now masses as much as a large office building. The structural stress is immense. Supports designed for 100 tons now bear 700. Some components begin failing. At 99.5%, 100 tons becomes 1,000 tons. 10 times heavier. You've crossed into thousands. Your ship weighs as much as a naval cruiser, as much as a large suspension bridge segment. The frame groans, metal fatigues, but somehow it persists. At 99.9%, 100 tons becomes 2,200 tons, 22 times heavier. Your spacecraft now masses as much as 3 fully loaded 747 aircraft, as much as a small office tower. Every rivet, every weld, every joint experiences forces it was never designed to withstand. At 99.99%, 100 tons becomes 7,000 tons, 70 times heavier. Your ship weighs as much as a World War II battleship, as much as a large apartment complex. The engines can barely move this mass. Acceleration becomes negligible. At 99.999%, 100 tons becomes 70,000 tons. Your spacecraft now masses as much as an aircraft carrier, as much as the largest ships humans have ever built. The energy required to accelerate this mass even slightly exceeds the total output of a nuclear power plant. At 99.9999%, 100 tons becomes 700,000 tons. Your ship weighs more than the Empire State Building, more than any single structure humanity has constructed. Its gravitational field affects nearby objects. Dust and debris spiral toward it. At 99.999999%, 100 tons becomes 7 million tons. Your spacecraft weighs as much as a large mountain, as much as a substantial asteroid. It would take the combined power output of every power plant on Earth to move it a single meter. Think about that. A spacecraft that started at 100 tons, roughly the size of a large bus, now masses as much as a mountain. And we're still not at light speed. still short by a fraction so tiny that expressing it requires 9 decimal places, still separated from that final barrier by a gap narrower than a proton compared to the width of the galaxy. The black hole problem, when gravity wins, but here's where the scenario transitions from difficult to catastrophic. At these extreme masses, something else happens. Something Einstein predicted in his general theory of relativity, published in 1915, a decade after his special relativity paper. Gravity isn't a force, it's a curvature of spacetime. Mass tells spacetime how to curve. Curved spacetime tells mass how to move. This creates the phenomenon we experience as gravitational attraction. More mass means more curvature. Extreme mass means extreme curvature. There's a threshold called the Schwarzschild radius. If you compress enough mass into a small enough volume, the space-time curvature becomes so severe that nothing can escape, not even light. You've created a black hole, a region where gravity has become so intense that it tears a hole in the fabric of space-time itself. For Earth, the Schwarzschild radius is about 1/3 of an inch. If you could compress Earth's entire mass into a sphere smaller than a marble, it would become a black hole. For the Sun, the Schwarzschild radius is about 2 miles. Compress the Sun down to the size of a small town, and it collapses into oblivion. For your 100-ton spacecraft, at rest, the Schwarzschild radius is incomprehensibly tiny, about 10 to the power of -23 meters. A decimal point followed by 22 zeros before you reach the 1, smaller than a quark, smaller than anything we can measure or even meaningfully imagine. But as your spacecraft approaches light speed, as its mass multiplies by millions, by billions, by numbers that exceed description, the Schwarzschild radius grows. At some point, the spacecraft's actual size becomes smaller than its Schwarzschild radius. At that moment, inevitably, catastrophically, your spacecraft collapses into a black hole. The exact velocity where this happens depends on the spacecraft's dimensions and density, but it will happen. Long before you reach light speed, your increasingly massive vessel will reach a critical threshold. Space-time will collapse around it. The ship, the crew, everything aboard will be crushed into a singularity, a point of infinite density where the laws of physics break down completely. Your mission to reach light speed ends not with triumph, but with gravitational collapse. Not with acceleration, but with annihilation. The universe protects itself from infinite mass by converting anything that gets too massive into a black hole. And black holes don't accelerate. They sit in space-time, warping it, consuming it, but they don't travel at light speed. They can't. The universal speed limit. Why this matters? This isn't speculation or theory. This is observed, tested, confirmed reality. Particle accelerators prove it every day. At CERN, the Large Hadron Collider accelerates protons to 99.99999% light speed. That's 7 nines after the decimal. At this velocity, the proton's mass has increased by 7,000 times. A proton that normally weighs 1.6 times 10 to the -27 kilograms now weighs 1.1 times 10 to the -23 kilograms. To accelerate these protons to this speed requires enormous energy. The LHC uses superconducting magnets cooled to near absolute zero. It consumes enough electricity to power a small city. And what does all this energy accomplish? It accelerates protons to 7 nines, not 8, not 9, 7. To reach 8 nines would require 10 times more energy. 9 nines would require 100 times more. 10 nines would require 1,000 times more. Each additional 9 multiplies the energy requirement by 10. The curve shoots toward infinity faster than any technology can follow. Scientists have been accelerating particles for decades. They've pushed electrons, protons, heavy ions, exotic particles to relativistic speeds. They've poured billions of dollars and countless hours into these experiments. And in all that time, with all that effort, with all that energy, they've never, not once, not even remotely, come close to accelerating anything to light speed. Because they can't. Because it's impossible. Because the universe has a speed limit, and that limit is enforced by the most fundamental laws of physics. Some people hear this and think, but what about antimatter? What about fusion? What about zero-point energy or quantum vacuum fluctuations or some exotic physics we haven't discovered yet? The answer is, doesn't matter. None of it matters. You could harness the total energy of a supernova. You could tap into the quantum foam. You could build a Dyson sphere around a black hole and capture all of its Hawking radiation. You could discover physics so advanced it would make Einstein look like a caveman, and you still couldn't reach light speed. Because the problem isn't energy availability. The problem is that as you approach light speed, the energy required approaches infinity. And infinity is not a large number that clever engineering can overcome. Infinity is a wall, an absolute barrier, a mathematical concept that represents more than any amount. You cannot have infinite energy. The universe doesn't contain infinite energy. Therefore, you cannot reach light speed. The logic is airtight. The conclusion is unavoidable. The philosophical weight, accepting our limits. This realization carries weight beyond physics. It touches on philosophy, on the human condition, on our place in the cosmos. We're a species that prides itself on overcoming obstacles. We've conquered diseases, tamed continents, split atoms, decoded genomes, built thinking machines. Every generation looks at the impossible achievements of the previous generation and says, we can do better. And usually, we can. But not here. Not with this. Light speed doesn't yield to determination. It doesn't respond to ingenuity. It doesn't care about human ambition or species-wide effort. It simply exists, immovable and eternal. Some find this depressing. The universe as a prison with bars made of physical law. Humanity trapped in a cosmic cage, forever separated from the stars, permanently isolated in our tiny corner of space. Others find it strangely liberating. Limitations force creativity. Boundaries provide structure. Knowing what's impossible allows us to focus on what's possible. We won't waste centuries trying to reach light speed because we know, with mathematical certainty, that it can't be done. This knowledge redirects our efforts toward achievable goals, and honestly, maybe that's healthy. Maybe a universe without limits would feel empty. Think about video games. When you enable cheat codes and become invincible, the game loses meaning. Challenge creates engagement. Difficulty creates reward. Limits create value. The light speed barrier ensures the universe remains vast. It preserves mystery. It guarantees that some questions stay unanswered, some horizons unreachable, some dreams unfulfilled. Is that tragic? Or is it what makes the cosmos worth exploring? Consider this. If we could travel instantly anywhere, would we? Would Mars feel special if it was a 5-minute trip? Would Alpha Centauri inspire wonder if we could visit on a weekend? Distance creates significance. Time creates meaning. Limits create appreciation. The fact that we cannot reach light speed, that we're fundamentally restricted to subliminal velocities, makes the stars precious. Every photon that reaches Earth from a distant galaxy has been traveling for millions or billions of years. That photon carries information across gulfs so vast they humble the mind. When we look at that light through our telescopes, we're seeing the universe as it was when that photon began its journey. We're observing the past. We're witnessing cosmic history. If we could travel at light speed, we could chase those photons. We could go back to their source. We could see those ancient galaxies as they are now, not as they were. We'd lose something profound in that capability. We'd lose the humility that comes from recognizing we're separated from the cosmos by time as well as space. Maybe the universe designed it this way deliberately. Maybe the speed limit exists not to constrain us, but to teach us. To remind us that we're part of something larger, something we didn't design and cannot control. To keep us humble, to preserve wonder. Or maybe the universe didn't design anything. Maybe these laws simply exist, emergent from deeper mathematics, arising from the fundamental structure of space-time. Maybe there's no purpose, no lesson, no meaning beyond the cold, hard equations. Either way, the result is the same. We cannot reach light speed because our mass would become infinite. This is reason number one. The first wall, the initial barrier, but it's not the only one. Mass is just the beginning. The universe has stacked multiple impossibilities on top of each other, creating a fortress of physical law that cannot be breached. Part 3. The energy wall and time's end. The energy equation, when numbers stop making sense. We've established that mass increases exponentially as you approach light speed. Now comes the second wall, and it's even more insurmountable than the first. Energy, specifically. The energy required to keep accelerating as your mass keeps growing. Remember Einstein's equation. E equals mc squared. Energy equals mass times the speed of light squared. We've already discussed how this equation converts between mass and energy. But there's another implication hiding in that simple formula. If your mass is increasing, the energy needed to accelerate you is also increasing, and not just proportionally, exponentially, catastrophically. Let's return to our 100-ton spacecraft. At rest, it has a certain amount of kinetic energy. Zero, actually, because it's not moving. To get it moving requires adding energy. The faster you want it to go, the more energy you need to add. At everyday speeds, this relationship is straightforward. Double the speed, quadruple the energy. Simple physics. Predictable mathematics. But at relativistic velocities, the equation transforms into something monstrous. The energy required doesn't just increase with the square of velocity. It increases toward infinity as you approach light speed. The same exponential nightmare we saw with mass applies to energy. Each additional percentage point costs exponentially more than the last. Let's put actual numbers to this nightmare. Real figures that demonstrate exactly how absurd this problem becomes. To accelerate our 100-ton spacecraft to 10%, light speed requires approximately 4.5 times 10 to the 18th joules. That's followed by 18 zeros. For quintillion 500 quadrillion joules. To put that in perspective, that's the total energy output of a large nuclear power plant running continuously for about 10 years. Difficult. Absolutely. Theoretically impossible. No, we could conceivably generate that much energy given enough time and resources. Now let's jump to 50% light speed. The energy requirement is approximately 1.3 times 10 to the 20th joules. That's 130 quintillion joules. That's all the energy humanity produces globally in about 3 years. Every power plant, Every engine, every battery, every solar panel, every wind turbine on Earth. Running for 3 straight years. Their combined output would equal the energy needed to push one spacecraft to half-light speed. Already we're approaching fantasy territory, but let's continue climbing the curve. 75% light speed requires approximately 3.4 times 10 to the 20th joules. That's about 8 years of humanity's total energy production. 8 years for one ship, carrying maybe a dozen people. 90% light speed. Now we need approximately 1.1 times 10 to the 21st joules. That's 1100 quintillion joules. That's the combined energy of every nuclear weapon ever built, multiplied by roughly 1000. Every bomb, every warhead, every explosive device humanity has constructed in its entire history, times 1000, detonated simultaneously. That's what you'd need to reach 90% light speed. Stop and consider that for a moment. We're talking about energy levels that dwarf anything humanity has ever harnessed. Energy that exceeds our entire industrial civilization's capacity by orders of magnitude, and we're only at 90%. We still have 10 percentage points to go. Comparing 2 stars, when the sun becomes your fuel tank, at 99% light speed, the numbers transcend human reference points. We need approximately 3.1 times 10 to the 21st joules to understand this scale. We have to start comparing to astronomical objects. The sun outputs about 3.8 times 10 to the 26 joules every second. Every single second, our star releases more energy than humanity has used in its entire existence. The fusion reactions in the sun's core are so powerful, so constant, so overwhelming that they're difficult to comprehend, and yet, reaching 99% light speed would require about 3 seconds of the sun's total output. 3 seconds of stellar power, bottled somehow, harnessed completely, converted perfectly into kinetic energy for your spacecraft. No losses, no waste, no inefficiency. And that's just to reach 99%. We're not done, not even close. 99.9% light speed requires approximately 9.9 times 10 to the 21st joules. That's about 10 seconds of solar output, 10 seconds of a star's fury, channeled into moving one vessel. 99.99%. Now we need 3.1 times 10 to the 22 joules, about 30 seconds of the sun's production, half a minute of stellar energy for a single spacecraft. Do you see where this is going? Every time we add another 9 after the decimal, every time we squeeze a bit closer to that ultimate velocity, the energy requirement multiplies by roughly 10. This isn't a linear progression. This isn't even exponential in the conventional sense. This is a mathematical cliff face, shooting toward infinity. 99.999% light speed needs about 99 seconds of solar output. A minute and a half of raw stellar power. 99.9999% requires approximately 5 minutes of the sun's energy. 5 minutes. 300 seconds. The amount of energy our star produces while you eat lunch, if you could somehow capture and store it all. 99.99999% needs 50 minutes. Almost an hour of the sun's complete output. An hour of fusion reactions, radiation, neutrino production, everything the sun does, captured perfectly. 99.9999999% requires 8 hours, a full work shift worth of stellar energy. 8 hours of the sun's 3.8 times 10 to the 26 joules per second output. The numbers have become so large, they're essentially meaningless to human cognition. And we're still not at light speed. We're incredibly close, unimaginably close. So close that the difference is measured in parts per trillion. But we're not there. And to actually reach there, to hit exactly 100% light speed, would require infinite energy. Infinity, the unconquerable concept. Let's talk about infinity. Not as a vague idea, not as a poetic concept, but as a mathematical reality. Infinity isn't a very large number. It's not a trillion, or a quadrillion, or a googolplex. It's not even a number at all, really. It's a concept that represents larger than any number you can possibly name or imagine. If you took all the energy in the observable universe, every photon from every star, every bit of kinetic energy from every moving particle, every quantum fluctuation in every cubic centimeter of space, and added it all together, you'd get a finite number, a stupendously large finite number, but finite nonetheless. That number is not infinity. That number, as incomprehensibly huge as it is infinitely smaller than infinity. Infinity minus 1 googolplex is still infinity. Infinity divided by a trillion is still infinity. You cannot diminish infinity through subtraction or division. You cannot approach it through addition or multiplication. This creates an impossible situation. To reach light speed requires infinite energy. The universe contains finite energy. Therefore, reaching light speed is impossible, not difficult, not unlikely, logically, mathematically, impossible. No amount of technological advancement changes this. You could discover a way to extract energy from the quantum vacuum. You could harness the radiation from black holes. You could build a Dyson sphere around every star in every galaxy. You could find a way to convert dark matter into usable power. None of it matters, because infinity is bigger than all of that combined. Infinity is bigger than a million universes, bigger than a Google universes. Infinity remains forever out of reach, no matter how much finite energy you accumulate. The universe has created a perfect trap, a speed that's theoretically reachable but practically impossible. You can get arbitrarily close. You can spend all the energy of all the stars and reach 99.999999999%. But that final infinitesimal gap, that last microscopic fraction, requires infinite energy to cross. And infinity is a wall no technology can breach. It's not an engineering problem. It's not a resource problem. It's a logical problem. You cannot gather infinite amounts of a finite resource. Time dilation, when clocks betray you. But wait, the problems compound. Let's talk about time. Specifically, time dilation. This is the third wall, and it's perhaps the strangest of all. Special relativity tells us that time is not absolute. It's not a universal clock ticking away the same for everyone, everywhere. Time is flexible, malleable, dependent on velocity. The faster you move through space, the slower you move through time. This isn't theory. This isn't speculation. This is observed, measured, confirmed reality. GPS satellites prove time dilation every day. They orbit Earth at about 8,600 miles per hour. At that velocity, time runs slightly slower for them than for us on the ground. The difference is tiny, about 7 microseconds per day, but it's measurable. GPS systems have to account for this time dilation, or they'd give inaccurate positions. The fact that your phone's navigation works is proof that time dilation is real. But GPS satellites are moving at a tiny fraction of light speed. What happens at relativistic velocities? At 10% light speed, time runs at 99.5% normal rate, barely noticeable. If you traveled for a year at this speed, you'd age about 2 days less than someone stationary. At 25% light speed, time runs at 97% normal rate. 1 year for you equals about 1 year and 11 days for Earth. At 50% light speed, time runs at 87% normal rate. 1 year for you equals about 1 year and 2 months for Earth. The difference is becoming significant. At 75% light speed, time runs at 66% normal rate. 1 year for you equals 1.5 years on Earth. You're aging noticeably slower. At 90% light speed, time runs at 44% normal rate. 1 year for you equals over 2 years on Earth. Time dilation has become dramatic. At 99% light speed, time runs at 14% normal rate. 1 year for you equals 7 years on Earth. You're aging 7 times slower than everyone you left behind. At 99.9%, time runs at 4.5% normal rate. 1 year for you equals 22 years on Earth. Leave for a decade, return to find 2 centuries have passed. At 99.99%, time runs at 1.5%. 1 year for you equals 70 years on Earth. Your mission duration, measured in years, translates to lifetimes for those at home. See the pattern. As velocity approaches light speed, time approaches zero. Not slow, not nearly stopped. Zero, completely frozen. At exactly light speed, from the traveler's perspective, time stops entirely. The photon's perspective, living in an instant. This creates a bizarre reality for photons. Light travels at light speed, obviously. For a photon, no time passes, ever. A photon emitted from the surface of the Sun travels 8 minutes and 20 seconds to reach Earth. From our perspective, from the photon's perspective, 0 time passes. The photon is created and destroyed in the same instant. It experiences no journey, no duration, no elapsed time between emission and absorption. Its entire existence, from its viewpoint, is instantaneous. It's born in the Sun's photosphere and dies in your retina simultaneously. Photons emitted from distant galaxies travel for billions of years from our perspective. They cross incomprehensible gulfs of space, journeying through cosmic voids, passing by galaxies and nebulae, until finally they slam into a telescope mirror on Earth. From our perspective, that's a multi-billion-year voyage. From the photon's perspective, instantaneous. No time elapses. This isn't just weird. This is reality-breaking weird. It suggests that the experience of time is fundamentally tied to velocity. Move fast enough, and time slows. Move at light speed, and time stops. Now, imagine you're in that spacecraft, somehow reaching light speed. From Earth's perspective, you're streaking across space at 186,000 miles per second. Time is passing normally for them. Seconds tick by. Minutes accumulate. Hours pass. From your perspective, nothing. Time has stopped. You're not experiencing seconds passing slower. You're not aging at a reduced rate. You're frozen. Locked in a single eternal moment. No thoughts form because thought requires time. No heartbeats occur because heartbeats require time. No existence happens because existence requires time. You're simultaneously traveling and stationary, moving and frozen, existing and not existing. It's a paradox, a logical contradiction, an impossible state. The movement paradox. How can you travel when time stops? Here's where it gets truly strange. Movement requires time. Going from point A to point B requires time to elapse. If no time passes, you cannot move. You're stuck at point A forever because reaching point B would require time, and you have no time. but you're supposedly traveling at light speed. By definition, you're moving, you're covering distance. You're going from one location to another, yet you're experiencing no time, which means you cannot be moving. These statements contradict each other. You're moving without time passing. You're traveling while frozen. You're covering distance in zero duration. It's logically impossible. The universe doesn't allow logical impossibilities. Reality has rules, and those rules include basic logic. Contradictions cannot exist. The universe resolves this contradiction by preventing you from reaching light speed in the first place. You can approach it. You can get arbitrarily close. But you can never actually reach it, because doing so would create a logical paradox. And the universe protects logic the same way it protects causality, by making the paradox-creating situation impossible. Think about what this means. Light speed isn't just a physical barrier, it's a logical one. Reaching it wouldn't just violate conservation of energy or require infinite mass. It would violate the basic principles of existence. It would require you to move without time, to travel without duration, to exist in a state that cannot exist. This is deeper than physics. This touches on the foundations of reality itself. Time is woven into the fabric of existence, so fundamentally that without time, concepts like movement, change, and causality become meaningless. Light speed represents the point where time ceases, and where time ceases, existence as we understand it ceases too. The subjective experience, what would it feel like? Let's try a thought experiment. Suppose somehow, impossibly, you reached light speed. What would you experience? From an external observer's perspective, you'd be zipping across space at maximum velocity. They'd see you moving. They'd watch you travel from Earth to Alpha Centauri in 4.3 years. They'd observe your journey, mark your progress, track your position. But from your perspective, nothing, absolutely nothing. Because experiencing something is time. Seeing requires photons to hit your retina, generate electrical signals, travel to your brain, and be processed into images. All of that takes time. No time means no sight. Thinking requires neurons to fire, synapses to activate, neurotransmitters to cross gaps between cells. All of that takes time. No time means no thought. Feeling requires nerve signals to travel from sensors to your spinal cord to your brain. Takes time. No time, no feeling. You wouldn't be unconscious. Unconsciousness is still a state that experiences duration. You wouldn't be asleep. Sleep happens in time. You wouldn't be frozen. Being frozen is a condition that persists through time. You'd be nothing, no experience, no awareness, no existence from your own reference frame. You'd be less than a statue because, at least a statue persists through time. You'd be a snapshot, a single instant stretched across space, with no internal experience whatsoever. Is that even life? Can something be called alive if it experiences no duration? If existence requires time, and you have no time, do you exist? These aren't just philosophical questions. They're fundamental problems with light speed travel. Even if you could somehow overcome the mass problem and the energy problem, even if you found infinite energy and developed materials that could withstand infinite mass, you'd still face this temporal paradox. You'd travel, but you wouldn't experience traveling. You'd reach your destination, but from your perspective, you never left. The journey would be instantaneous, which means it wouldn't be a journey at all. You'd be simultaneously at the start and end point, existing in both places and neither place, trapped in a logical impossibility. The comparative scale, humanity versus stars. Let's zoom back out and look at the bigger picture. We've talked about energy requirements in abstract terms. Let's make it concrete by comparing what we can do versus what we'd need to do. Currently, humanity generates about 18 trillion watts of power at any given moment. That's 18 terawatts. Sounds impressive until you realize that's about 1/10,000th of 1% of the sun's output. We're not even a rounding error compared to stellar energy production. The entire energy humanity has used throughout its existence, from the first fires to modern nuclear plants, totals about 5 times 10 to the 21 joules. That's accumulated over thousands of years. That's pyramids and cathedrals and factories and cities and wars and everything else we've ever done. Reaching 99.99% light speed requires approximately 3 times 10 to the 22 joules. That's about 6 times more energy than humanity has used in its entire history. For one spacecraft, one flight, one journey, we'd need to increase our energy production by factors that make ambitious seem like an understatement. Not double or triple. Not even 10 times or 100 times. We'd need to harness energy on stellar scales. We'd need to build Dyson spheres around stars, or tap into black holes, or discover physics so revolutionary it would make our current understanding look primitive. And even then, even if we achieved all that, we'd only reach some percentage of light speed. We'd get close. Incredibly close. But never there. Never exactly 100%. Because that final gap requires infinite energy, and infinity is not achievable no matter how advanced we become. The cold reality, 3 walls down, 2 to go. We've now encountered 3 fundamental walls preventing light speed travel. 3 distinct reasons why it's impossible, each sufficient on its own to create an insurmountable barrier. Wall 1, your mass becomes infinite. Physics doesn't permit infinite mass. The universe would collapse into a singularity. Can't happen. Wall 2, you need infinite energy. The universe contains finite energy. Cannot accumulate infinite energy. Can't happen. Wall 3, time stops completely. Movement requires time. Cannot move without time passing. Can't happen. Any one of these would be sufficient, but the universe doesn't rely on a single defense. It's stacked multiple impossibilities on top of each other, creating a fortress of physical law that cannot be breached through any means. And we're not done. We still have 2 more walls to explore. 2 more reasons why light speed travel is impossible. 2 more fundamental barriers built into the structure of reality itself. The next wall involves causality, the sacred principle that cause must precede effect. Light speed travel threatens this principle in ways that create logical paradoxes so severe they'd tear apart the fabric of reality. The final wall is perhaps the most profound. It involves the fundamental structure of space-time itself. The revelation that light speed isn't really about light at all, but about something deeper, something more fundamental to existence. These aren't just obstacles, they're lessons. The universe is teaching us something through these barriers. It's showing us our place, our limits, our cosmic boundaries. Some might find that depressing. Others might find it strangely comforting. Either way, it's the truth. And truth doesn't care about our feelings. It just is. Part 4. When causality breaks, the sacred order, cause, must precede effect. There's a principle so fundamental to reality that we rarely even think about it. Causality, the ironclad rule that every effect has a cause, and that cause always, without exception, happens before the effect. Never the other way around. You drop a glass, it falls, it shatters. The dropping causes the falling causes the shattering. The sequence is locked, unchangeable, sacred. You cannot have the glass shatter before it falls. You cannot have it fall before you drop it. The order is fixed. Fire burns your hand. The burning happens because you touched the flame, not before. Thunder follows lightning. Seeds grow before they become trees. Birth precedes life, precedes death. This ordering defines how reality operates. It's the backbone of existence, the foundation upon which physics, chemistry, biology, and every other science is built. Causality isn't just a law, it's the structure of time itself. The arrow of time points from past to future precisely because causes precede effects. Remove causality, and time loses meaning. Past and future become interchangeable. The universe dissolves into chaos. Now here's the problem. Faster than light travel threatens causality. Not metaphorically, literally. If you could exceed light speed, you could create situations where effects precede causes, where consequences happen before actions, where the future influences the past. The tachyonic anti-telephone messages from tomorrow. Physicists have explored this through thought experiments. One famous example is called the tachyonic anti-telephone. It's a hypothetical device that sends messages faster than light. Let's see what happens when you use it. You're on Earth. Your friend is on Mars. Currently, at this exact moment, both your clocks read 12 noon. Perfect synchronization in your reference frame. You send a message at 12:01 p.m. Earth time. The message travels faster than light, arriving on Mars at 12:02 p.m. Simple enough, right? Your friend receives your message 1 minute after you sent it. Cause precedes effect. Everything seems fine, but here's where special relativity creates havoc. According to Einstein's equations, observers in different reference frames disagree about simultaneity. What's now for you isn't necessarily now for someone moving relative to you. Time is not absolute. In certain reference frames, particularly those moving at high velocities relative to Earth and Mars, your faster-than-light message arrives before you sent it. From those perspectives, your friend receives the message at 11:59 a.m. while you send it at 12:01 p.m. The message arrives 2 minutes before it was sent. Effect precedes cause. The universe has broken its most fundamental rule, the grandfather paradox, reality eating itself. This leads directly to the famous grandfather paradox. If you can send information backward in time, you can create logical contradictions that destroy causality entirely. Here's how it works. You receive a message from your future self warning you about a disaster. You take action to prevent the disaster. The disaster never happens, therefore, your future self never experienced it. Therefore, your future self never sent the warning. Therefore, you never received the message. Therefore, you never prevented the disaster. Therefore, the disaster happens. Therefore, your future self sends the warning. Loop, contradiction, paradox. The timeline eating its own tail. The classic version involves time travel to the past. You go back and prevent your grandfather from meeting your grandmother. You're never born. But if you're never born, you can't travel back in time. So your grandfather meets your grandmother. You are born. You travel back in time. Round and round, an infinite loop of logical contradiction. The universe cannot tolerate these paradoxes. Reality must be self-consistent. Causes must precede effects. The timeline must be stable. These aren't preferences. These are requirements for existence to make sense. The causal barrier. How the universe protects itself. So how does the universe prevent these paradoxes? Simple. It makes faster than light travel impossible. The speed of light isn't just a velocity limit for matter. It's the speed of causality itself. It's the maximum rate at which cause and effect can propagate through space-time. Information cannot travel faster than light because information is causally linked. If you learn something, that knowledge was caused by observation or communication. Causes and effects chain together, creating causal links. These links cannot exceed light speed without breaking causality. Think of space-time as a fabric. Causality is the weave pattern that holds that fabric together. Pull one thread faster than light speed, and the entire weave unravels. The fabric tears. Reality itself becomes inconsistent. Light speed is the universe's defense mechanism. It's a firewall protecting causality from paradoxes. It's a fundamental speed limit, not because of energy or mass or engineering constraints, but because exceeding it would create logical impossibilities. And the universe doesn't permit logical impossibilities. Some people hear this and think, but what about quantum entanglement? Particles can affect each other instantaneously across any distance. Isn't that faster than light? Yes and no. Entanglement is instantaneous, but it cannot transmit information. You can't use entangled particles to send messages. The correlations appear faster than light, but no causal influence travels between the particles. Causality remains protected. The universe has loopholes, but those loopholes don't allow causality violation. The philosophical weight, time's arrow, cannot bend backward. This is reason number 4. This is the fourth wall. Even if you could somehow overcome infinite mass, infinite energy requirements, and time stopping completely, you'd still face this barrier. Faster than light travel breaks causality. Broken causality breaks logic. Broken logic. The universe prioritizes consistency over human ambition. It chooses logical coherence over interstellar convenience. It protects the arrow of time, even if that means limiting our cosmic reach. Think about what this reveals about the nature of reality. Causality isn't just important, it's mandatory. It's baked into the structure of existence so deeply that the universe will enforce speed limits, manipulate time, and create seemingly arbitrary barriers just to prevent causality violation. This tells us something profound. Time has a direction. That direction is sacred. The past influences the future, never the reverse. This asymmetry defines our experience of existence. Memory versus anticipation. History versus possibility. What was versus what might be. Without causality, none of these concepts make sense. Without the guarantee that causes precede effects, science becomes impossible. We couldn't learn from experience because past events wouldn't reliably predict future outcomes. We couldn't make plans because our actions wouldn't reliably create consequences. We couldn't exist as conscious beings because consciousness requires temporal continuity. The light speed limit protects all of this. It guards causality, which guards logic, which guards reality itself. 4 walls down. 1 remains. Part 5. The speed of reality itself. The 5 walls. Summary and reflection. We've journeyed through 5 fundamental barriers, 5 walls standing between humanity and light speed travel. 5 reasons why we will never, not with any technology or any breakthrough, reach that cosmic speed limit. Wall 1. Mass becomes infinite. At light speed, your mass would equal infinity. Infinity cannot exist in physical reality. The universe prevents this by preventing light speed. Wall 2. Energy becomes infinite. Reaching light speed requires infinite energy. The universe contains finite energy. Therefore, light speed is unreachable. Wall 3. Time stops completely. At light speed, time ceases. No time means no movement, no thought, no existence as we understand it. The paradox prevents the situation. Wall 4, causality breaks down. Faster than light travel creates scenarios where effects precede causes. The universe protects causality by limiting velocity. Wall 5, light speed is spacetime's update rate. Going faster would mean exceeding reality itself. You cannot exist outside existence. Not one of these is about engineering. Not one is about technology. They're about the fundamental laws of physics, the constitutional rules of reality, the non-negotiable structure of existence. The final word, the universe always wins. 5 walls, 5 fundamental reasons, 5 laws of physics that cannot be circumvented, bypassed, or broken. We can get close to light speed, 99%, 99.9%, as many nines as G allows, but never exactly 100%, never that final, infinitesimal gap. That gap is defended by infinity, by paradox, by the structure of space-time itself. It's a wall made not of matter but of mathematics, not of atoms but of logic, not of substance but of existence. We've explored the boundaries of possibility. We've traced the edges of what reality permits. We've discovered that some dreams, no matter how inspiring, remain forever out of reach. Not because we lack determination, not because we lack intelligence, but because the universe has drawn a line and said, this far, no further. And perhaps that's exactly how it should be. Perhaps perfect knowledge of our limits allows us to focus on what's actually achievable. Perhaps accepting impossibility is the first step toward achieving possibility. Perhaps wisdom lies not in fighting unchangeable laws, but in understanding them, respecting them, and building our future within their boundaries. Light speed stands as a monument to physical law, immutable, eternal, absolute. A cosmic speed limit enforced by the deepest principles of reality. We can rage against it. We can dream of exceeding it. We can spend centuries trying to break it. But in the end, the universe always wins. It has infinite patience, infinite time, infinite enforcement. The laws of physics are not suggestions. They're not challenges to overcome. They're the rules of the game, and we're all playing by them, whether we like it or not. This is the truth. The hard, cold, undeniable truth. We will never travel at light speed. The universe says no. And the universe always gets the final word.